I was told over lunch that one of the things that Alonzo Church used to do when he began his lectures was he would spend the first 5 minutes patiently and thoroughly cleaning the board. And I suppose he was collecting his thoughts while he was doing that. And that's probably a good idea. Maybe I should have followed his lead rather than enlisting help here and jumping right in, but I'm going to pursue a different course here. Okay, category theory. What is category theory and why do I need to know something about it? Not I, but you. Category theory is, as a first approximation, it's the abstract algebra of functions. Okay, let that sink in a little bit. It's the abstract algebra of functions. And of course, one of the themes of this meeting, and of course one of the themes of theoretical computer science, is that the lambda calculus is a calculus, a formal calculus for manipulating functions, for specifying, manipulating, and calculating with functions. So it's not surprising that there should be some kind of connection there, right, between category theory and lambda calculus. And of course, there is, in fact, a very deep connection. We're looking at the same thing, essentially, from two different points of view. Once from a kind of logical point of view on the lambda calculus side, and once from a more mathematical, if you will, or algebraic point of view coming from the category theory side. And really, these are just two different ways of looking at the same structure, the same idea, and they're complementary. And that's what's so fascinating about this connection is you can look at this same thing in these two different ways, the algebraic way or category theoretic way, which actually has a kind of geometric character, which you'll see as we get going, or the logical syntactical way. And those two different points of view are complementary, and they feed off from each other, and they suggest some interesting results. So that's the kind of background there, motivation for learning and using category theory in this setting that's so far removed from the original source of category theory in algebraic topology and homotopy groups and homology groups and all that stuff. So it's amazing that category theory has filtered through the rest of mathematics, even into theoretical computer science, and now it's really a kind of foundational discipline with these deep connections to logic. Okay, so let's look at the algebra of functions. What do I mean by functions? Well, let's just start out. So what I really mean is abstract functions. I mean any kind of process or assignment or procedure or expressions which can be read in a functional way. So it's the abstract algebra of abstract functions, if you like. But let's start out just by thinking of familiar set theoretic functions on sets in order to arrive at the basic principles of category theory. So we'll look at functions. We'll look at functions on sets. So suppose our sets, I'll write them with capital letters here. These are just some sets, right? And then a function, f, I'll write like this, going from A to B. So that's just to remind you that's a subset of the Cartesian product of A and B, which is therefore a relation on A cross B, right? So f, so here, officially, so in set theory, if you want to be formal about it, in set theory, what is a function from A to B? Well, it's really a subset of pairs, right, such that, and then we have the usual condition, right, for all A and A, there's a unique B in B such that the pair A, B is an element of that relation F. So that's the official definition of a function, but we're not going to really use that. I'm just going to think of functions in the kind of intuitive way of taking an element of this set and returning an element of this set. Good? How do functions behave? What operations are there on functions? Well, the basic operation that we're interested in category theory is this. If I have a function f from A to B, and I have another function g from B to C, then there's this operation of composition, g, which I write g after f. And the way that g after f works is, of course, g after f applies to an argument x from A to give me g applied to f applied to x. So that's the basic composition operation that we're interested in. And then there's another operation which is even simpler, and that is the identity function. That is, for each set A, there's an identity function, which I'll write like this, 1 sub A on A, and 1 sub A for any element x is just x. It's the usual identity function. So that's the basic data. We have a composition operation, and we have the identity function operation. And then we have some laws, and the laws look like this. If I take a situation like this, I have f, g, h, and first I compose like this, g after f, and then I compose the whole thing with h, so that's h after g after f. Or first I do this, that's h after g, and then I compose this whole thing, and that's h after g after f. Then the result, h after g after f, is equal, regardless of which way I do the composition. Because if you just unwind this formula, you see that both of those things are equal to h of g of f of x, right, for every x. So these things are equal. That's the associative law for the composition operation. And then the other law is if I take A, and I take any f like this, and I take here the identity on A, well, then this composite, f after the identity on A, is equal to f. And similarly, if I take here the identity on B, and I compose, then this composite, 1b after f, is also equal to f. Right? Because this function doesn't do anything. Right? So I take the x to x, and then I apply f. That's the same as just applying f. And similarly, this function doesn't do anything. So those are the basic laws, and that's really all the structure of sets that we want to use or make use of in our definition of a category. The idea is now we abstract away from all the rest of the things that you know about sets, subsets and Cartesian products and elements of elements and power sets. We forget about all that junk, and we just look at these algebraic operations. So how do you go about abstracting away from a mathematical point of view? Well, you give an axiomatic description of the structure you're interested in, which captures this much of the situation, but then you look at anything that satisfies that axiomatic. And that's how you abstract away from the specifics of this particular example. So the general definition of a category is an abstraction from this example. The definition of a category is this. Well, first of all, it consists of two kinds of things, and they're different. It's a two-sorted theory, technically speaking. There are the objects of the category, which are playing the role of the sets in this example, and there are what we'll call the arrows of the category, which are playing the role of the functions in this example. So I'm going to just keep with that same notation. So I'm going to write the objects with uppercase and in general, and I'll write the arrows with lowercase. And in addition, there's some more data in the definition of a category, namely, so for each arrow f, there are given objects called the domain and the codomain of f. So this was kind of implicit in this, but if I have a function, then it goes from some specified set to some other specified set. So we're going to put those in as explicit operations, and the notation will be this. So the domain of f is on the left of the arrow, the codomain is on the right. And we write f goes from the domain to the codomain. And then for each object, A, there's an assigned an arrow. So here's the identity arrow, 1 of A. And it, of course, goes from A to A. That's its domain, and that's its codomain. And then the axioms. So this is the data, and then we have the axioms, if you like, or the laws Well, those are just these laws that I just wrote down right here. Associativity and unit. Unit. So the axioms are just those two laws. It's H after G after F is H after G. After F, whenever those composites make sense. Composition is only defined when things line up, yeah? Oh, sorry, I forgot to put in the composition. Let me put that in. Oops. There's one more operation, composition. For each composable pair, that is, arrows like this, where the codomain of this one is the domain of this one, we have a composition operation, G after F, going from A to C. So that's one more bit of data, is this composition. So identity, composition, domain, and codomain. And then I have, as I said before, just the laws. The laws are associativity. So that was H after G after F is H after G after F, and the unit law. So that's 1 B after F equals F after 1 A. Okay, so that's the definition of a category. It captures this example as we just checked. Yep. Yeah, okay. Yep, sure. Thanks, yep. As we just checked, it captures this example. We just looked and saw that this example satisfies these conditions. So our first example of a category is the category which I'll call sets, that has the objects are sets and the arrows are functions. Let's have some more examples of categories, because there are lots and lots of examples. This was just kind of a place to start. Well, there are some interesting finite categories, just to give you a different flavor here of what's going on. For example, there's the category 1, which has one object, which I won't even bother to give a name, and it has one arrow, namely the one it has to have, its identity arrow. So that's what it looks like there. Now you're thinking, well, what is that object? I'm saying, just take something and call it an object of this category. Put in formally any other thing, call it the arrow of the category, right? Define the domain and codomain in the obvious way there, and that's it. You don't have to compose anything. I mean, this is composable with itself, but of course, all the composites are equal to itself by the unit law, so we're done. There's a category 2. It has two objects. I'll give them different names, like that, and it has one arrow between them. Now I should put in these identity arrows, but they don't really do anything, and there's no other composition around. So that's it. That's the category 2. And similarly, there's a category 3. Now you can kind of guess how this is going to go on, right? It has these arrows. It has these identity arrows, which I won't draw after this example. And then there is a composite that you can make. Let me put that in. And then nothing else. There are no more composites to be made, and we're done. So that's the category 3. That looks like a B, doesn't it? 3. There's another category 0, the empty category. It looks like this. It has no arrows and no objects. Okay? And so now you get the idea, right? You can make any kind of crazy. You can make lots of finite categories. You just say, take some objects, let's call them A, B, C, D. Put in some arrows, but make sure that any time you've made a composable sequence, you have to say what the composite is going to be in order to specify your category. And you can make finite categories like that very easily. So there are lots of finite categories involving some finite family of objects and some finite collection of arrows, and then you define your compositions and identity operations. So that should give you a sense of how many different kinds and simple kinds of categories there are. Let's look at some other more natural kinds of categories. So for example, there's a notion of a poset, partially ordered set. Everybody know what a poset is? partially ordered set. Everybody knows, almost everybody knows what a partially ordered set is. So let's suppose I have a poset P. It has a partial order on it. That's a reflexive, transitive, and antisymmetric relation on the set P. And I'm going to make it into a category. Poset category. Like this, I'll say, given some elements P and Q, I'll say there's an arrow from P to Q just in case P and Q stand in this relation, PQ. So because of the way I've defined this, there's at most one arrow between any two objects. So I put formally in an arrow just in case these things stand in that relation. Why is this a category? Well, the identity arrow is in there because of the reflexivity of the relation. The composition is in there because of transitivity of the relation. You don't have to wonder what is the composite. It's there because there is at most one arrow between any two things, and there is one by transitivity. Okay? And what about the laws? Here's a little check. What about the unit and associativity laws? How do I know that they hold? Keep trying. Yeah, there's at most one arrow between any two objects. So the laws are equations among arrows, right? If I have here P, Q, R, associativity, for example, looks like this. And now it says P, Q, R, S. And associativity says, take this arrow, compose it with that, and compare it with this arrow composed with that. And it says these are supposed to be equal. But any two arrows between given objects are equal in a partially ordered set. And so the associativity law holds for free. And similarly, the unit law will hold for free. Okay? So a poset is a category in this kind of trivial or degenerate way, if you like. It's a category with few arrows. Few arrows. By which I mean at most one between any two things, P, Q. A kind of complementary phenomenon is a category with very few objects and lots of arrows. This one has lots of objects, perhaps, and very few arrows. Let's take a monoid, M, with a multiplication operation and a unit element as a category. Who knows what a monoid is? Oh, great. Okay, almost everybody. It's like a group without inverses, right? If you know what a group is, groups have inverses, like the additive group of the integers, right? Has the negative numbers. If you just take the positive numbers, 0, 1, 2, and so on, the natural numbers, that's a monoid under addition with the 0. So a monoid can be regarded as a category. Objects, well, there aren't really any objects in there. Namely, we just put in a formal object. So we'll go like that. A formal object. And then we regard the elements of the monoid as arrows on that formal object. So for every element of the monoid, we put in an arrow. And now, because this arrow has the same domain and codomain, right, any two things are composable. Yeah? And so if I have M here and I have some N here also coming from the monoid, well, then I have to make a composite. What should it be? I'll just take the group multiplication or the monoid multiplication there, and that will be my formal composite of these two elements. And finally, I'll take the unit of the monoid and make that my identity arrow. Good? So now I have identity, I have composition, I have arrows and objects, domain and codomain are obvious, and now I have to check the laws. So what about the category laws now? What about the unit law? Well, that comes from the unit law of the monoid, right? The U acts as a unit for the product, but the product is composition. What about the associativity law for composition? Well, that comes from associativity for the product and the monoid. It's part of the definition of a monoid is that the product is associative. So I get those for free, basically, by the fact that I've assumed I've got a monoid. So a monoid is then a category, but it's a special one. It's a category with just one object. And in fact, it's exactly a category with just one object, right? You can interchange those two concepts. They're the same thing. A category with one object only is exactly the same thing as a monoid. Good? Say again? Right. So that's a trivial monoid. That's a trivial monoid that just has a unit element. It's a trivial monoid. It's the same category. Okay? Right. The notion of maybe the first structural notion in category theory, or notion that can be defined entirely in terms of the language of categories, but a very useful and important mathematical notion, is the concept of isomorphism, right? You've encountered isomorphism in lots of different ways. Sometimes people say things are isomorphic if they have all the same properties. It's not really right. I mean, it's true, but it's not the definition of isomorphism. The definition of isomorphism is a category theoretic one. So in any category, objects, so let's do it this way. An isomorphism from A to B, let's say F here, is the following. It's a map A, it's a map F from A to B together with, or depending on how you want to do things, such that there exists a map G coming back such that G after F is the identity on A, right? That makes sense. G after F is the identity on A. And F after G is the identity on B. F is the identity on A. F after G is the identity on B. Look, it only uses the concepts of category theory, composition, identity. So now, if you give me a category, I can tell you what the isomorphisms are in that category, right? For every category, there's a canonically determined notion of isomorphism in the category. So if you look at, well, we don't have enough examples here yet to see what isomorphisms are. In sets, isomorphisms are bijections of sets. In a poset, well, isomorphisms will be what? It will be P and Q such that P is less than Q and Q is less than P. So it'll be identity in a poset. Isomorphism is identity. What about in a monoid? What is an isomorphism in a monoid? Yeah, it's an element of the monoid that has an inverse. So monoid M, suppose we have some little m in here, which is an iso in the monoid. That means there's some element, let me call it M inverse, such that this is the unit and this is the unit. So an element, an invertible element, an element with an inverse. And in fact, it's easy to show that inverses are always unique when they exist. So maybe you're familiar with the definition of a group. So a group is a monoid, so a category with just one object, monoid in which every element, every m in M has an inverse. So a group is a category with one object in which every arrow is an isomorphism. It's the same thing as the usual definition of a group that you've seen using equations and operations. Okay? Okay, yeah, that's the second time I've been asked. Just keep asking and hopefully it will happen. Yep.
What? Don't keep asking now.
Remind me from time to time. Okay. Okay. So those are some examples. But that's only one kind of example. They're kind of degenerate in a sense, right? Because these had lots of objects but only a few arrows. This has just one object and possibly lots of arrows. Let's look at some more kind of general examples. And now, in fact, we have the material to build some examples, even if you're not familiar with them. We can make the category of all posets. So what is an object is a poset. Objects are posets, partially ordered sets. Right. And the arrows, well, these will be functions that preserve the ordering, or take the ordering here to the ordering over here. So those are usually called monotone maps. Monotone maps. So that is, if P is less than or equal to P prime, then F of P over in Q is less than or equal to F of P prime, where this is the ordering on P, and this is the ordering on Q. So that's the notion of a monotone map. And that makes a category because basically we're taking certain functions, right? And then we define the associativity, we define the composition to be composition of functions. We define the identity to be identity of functions. You have to check that the composition of monotone maps is again monotone and that the identity map is monotone. But once you do, you get the laws for free from the laws for sets. So that's an example there. What about the category of monoids? Yeah? A lot. Okay, good. Really? Okay, wow. Maybe I should write with 2 magic markers. It's blackboard bold. Yeah? Okay. So there's the category of monoids. So the objects, is that better? Objects are monoids, M, N, etc. And the arrows are homomorphisms of monoids. They look like this: F, M, arrow, N. They look like they're homomorphisms. I have to squeeze this in the corner, so it's going to, this one is an exception. It's going to be a little smaller. Homomorphisms of monoids. What's a monoid homomorphism? Well, it says F of M times N equals F of M times F of N. And F of the unit is the unit, right? It's a usual notion of an algebraic homomorphism of algebraic structures. And so that gives me a category 2, basically for the same reason that monotone maps give me a category. Good? And now there are lots of other examples. Here, I'll give a fresh start here. Lots of other examples. Any kind of structured set together with homomorphisms of that structure, right? So things like groups, rings, if you're familiar with these algebraic structures. What about pointed sets? So we could have like sets with a point. That would be, the objects would be pairs consisting of a set together with a distinguished element, and the maps would be functions that take the distinguished element to the other distinguished element. There are lots of examples like that. Or posets with a bottom, and then the maps have to preserve the least element in the poset. Or posets with a, say, a join operation on the elements, and then the maps have to preserve the joins, and so on. So all kinds of examples of structured sets give rise to familiar categories. Of course, there are the more traditional ones, like the category of topological spaces, the category of differentiable manifolds and smooth maps, and on and on and on. So there are lots of examples of categories like that. Not to give you the impression that the arrows in a category are always supposed to be functions. That's a popular misconception coming from these kinds of examples. You could have, for example, the category of relations where the objects are sets, but the arrows are relations. So an arrow R from A to B is a relation, arbitrary, not functional, on A cross B. And then you have to come up with a clever way of defining composition of relations. And so that's an example that you see sometimes. If you look in, oh, I forgot to say, there are lecture notes on the web. There's also a whole PDF of a whole book. My book is on the web for you to use. Please don't put it on Wikipedia, okay? Just use it for this class, but don't circulate it. I've had to take it off from Wikipedia several times. So, and you can see these kinds of examples worked out. So there are lots of examples of categories where the arrows are not functions. See if there's anything else I wanted to be sure to mention. Oh yeah, here's another kind of example. This one is going to be a homework exercise. It's an example of a very different kind. It's a category of proofs. Category of proofs. Let's suppose we have some deductive system of logic. System of logic, could be propositional logic, let's say. And let me write and have some formulas. I don't have to be very specific about this. So I have some formulas. And then I have a notion of deduction of formulas. And I do need to have deductions. I do need to have deductions from premises, just to make things simple. So let's say I have a notion of a deduction like this. I go from here to here. And I want to consider this deduction. Let me call that P. So maybe it's this notion. But it's not just the notion of deducibility. It's deducibility by a particular given deduction that takes me from the assumption phi to the conclusion psi. Maybe it's a system of natural deduction, and the idea here is you've canceled all the premises but one, right? Or you can come up with other formulations there. You could have an axiomatic Hilbert-style system or whatever. Okay? So now you can guess what the objects and the arrows are going to be. These are the objects. These are the arrows in our category. Okay? How will we do composition? Well, let's suppose we have a deduction like this. So that's P. And then we have another one here. To be composable means these things line up. So here's a conclusion in this deduction. Here's an assumption in this deduction. We do the obvious thing now. We plug this in for this. The composition of these two things is going to be the deduction that starts from phi, goes down to psi, and then keeps on going and ends in theta. So that's the composition. It's that obvious deduction. The unit deduction is the trivial proof there that assumes phi and concludes phi at the same time. That's the unit. That's one phi. So is this a category? Looks pretty good, doesn't it? We've got the objects, we've got the arrows, we've got the domain and the codomain. We've got the composition, we've got the identity. So now we just have to check the laws, right? So how about the associativity? Is this operation going to be associative? Yeah, you can just look at it and see that it's associative, right? It's plugging things together. It's obviously associative. What about this? Does this satisfy the unit law? Yeah, it does. It's obviously a unit for that operation. So there's a nice category. And an interesting thing about this category, unlike, we could define a category like this too, by saying define the ordering on the formulas of deducibility, not deductions. That's obviously well, it's not quite a partial ordering. It's what's called a pre-order because it's missing the anti-symmetry condition, but it's basically a pre-order. Then it would be a pre-ordered or partially ordered category like that. There would be at most one arrow between any two objects. That wouldn't really be the category of proofs. That would be the category of provability, or the category of formulas, or something like that. This is a much more interesting category, right? This category has the whole proof theory of the system in it, because different proofs are different arrows. This thing is not a poset or pre-ordered category. you can have many different proofs between two formulas, and those are different arrows between those objects. Yeah? So this category can have a very interesting and rich structure, and in fact it does in general. Even in something as simple as a positive fragment of intuitionistic logic, intuitionistic propositional logic, just the positive fragment with conjunction and implication, that has a very rich proof theory. It's basically the simply typed lambda calculus. So in this category. So we'll get to that, I hope, in the next lecture. I'll be able to explain that. Okay, so that's enough enough for examples. Now what I'd like to do is look at some constructions that give us new categories out of old. There are, billions and billions of categories out there, and we can only get a glimpse of a couple. But even at that, once you get started, then you can make lots of new categories out of old categories. And that's what we're going to do next. So some constructions on categories. Let's look at some constructions. Oh, that's better. Even I can see that better. Constructions on categories. Let's try a product category. If I have a category C and another category D, I'm going to make a product of those two categories. So the objects are going to be pairs C, D, with C from C and D from D. And the arrows are going to be just pairs of arrows, let's say F, G, with F going from C to C prime and G going from D to D prime. And then I'll do the identity arrows. So the domains and codomains are the obvious ones that I've written down here. The identity arrow is just the identity in both components, right? So the identity on the pair C, D is just the pair 1C, 1D. And similarly, the composition of, let's say, F prime, G prime is just going to be component-wise. F, G is just F prime, F, G prime, G. So I just do things component-wise, and then, of course, everything works out. I get the laws, the category will work out for free. And that notion of the product agrees, of course, with the product of groups, the product of post sets, and so on. And we're going to see next time that that's not just an accident, that's actually determined by the laws of products in general. Another example of a construction on categories is the arrow category. So given a category C, the arrow category of C has as objects are the arrows of C. So let me say A, F, A prime, arrows of C. Arrows. And the arrows, those are the, oh, I forgot to do something. Let me go back in a minute. The arrows are going to be F, A prime. Here's another one, B, G, B prime. So those are two objects, and an arrow between these two objects is going to be a pair of arrows like this, making a commutative square. That is, a pair of let me say, this arrow, I'll call it alpha. It has a first component and a second component, alpha 1 and alpha 2, or let me say, notation's not good, sorry. Yeah, okay, alpha 2, such that by commutative square, I just mean going around both ways gives the same thing, right? Alpha 2 after F equals G after alpha 1. So an arrow in this category is a commutative square in C. An object in the arrow category is an arrow in C. An arrow in the arrow category is a commutative square in C. Okay? It's just kind of a compound operation there. And obviously, you can keep going in that way. Do I have another board here? No, I used that. I forgot a very important thing. How could I forget that? I should have squeezed in here something else. So the motto of category theory, I guess, something like that. The motto or the slogan. The slogan of category theory is Somebody want to guess what the slogan of category theory is? It's something like, it's the arrows that count, right? Not just the objects, but the arrows. The relations among the objects are given by mapping one to another. That's what the arrows do. They map one object to another. And that's what really determines the structure of the objects, is the way you can map them or relate them to each other. So the arrows count. So of course, the first thing you should ask if somebody gives you some new kind of mathematical structure or logical construction is, what are the maps between them? What are the arrows between them? Because that tells you what parts of the specification are relevant, right? Sometimes you specify some new kind of structure or data type or something in a way that requires a bunch of auxiliary machinery, but you don't really care about all that. You only care about certain aspects of it. But to care about an aspect is something in your head, right? It's not a mathematical thing. To make it into a mathematical property, you specify what the arrows are. And the arrows will then determine what aspects get preserved, what aspects count, and what aspects can be thrown away or don't count. So given that, as soon as I've defined over there what a category is, you should ask me, what are the maps of categories? Right? And that's a functor. So a functor, that's the idea of a map of categories. Functor F from one category C to another category D, what is that? Well, just like a category has two parts, objects and arrows, a functor also has two parts. So officially, although I'll never write this again, it has a part that takes the objects of C to the objects of D, so it's a mapping. And then there's this other part, the arrow part. Let me say, this is the object part, this is the arrow part, which takes the arrows of C to the arrows of D, plus some laws which are best illustrated diagrammatically. That is, if I have here A, F, B, G, C, and then here's the composite G after F, and here, say, is the identity on A, and I apply the functor F, so this whole diagram is living in the category C. I apply the functor F, I get something over here in the category D. It looks like this. Well, the functor applies to objects to give new objects. It applies to arrows to give new arrows. And a condition is it preserves domains and codomains. So the domain of this arrow is this, the codomain is that. Therefore, because the functor is required to preserve domains and codomains, this will all line up. And then the further condition is, well, as you might guess, it preserves identity maps. So the identity, the F applied to 1 of A, is required to be equal to 1 of F of A. And finally, it preserves composition. So F of G after F is required to be equal to F of G after F of F. So it just preserves all the data in the definition of a category. That's what a functor is. Preserves the objects, the arrows, the domains, the codomains, the composition, and the identity maps. Okay, so that's the basic notion of a functor. And now let's observe that, for example, here, there's a functor from the product category down to C. It's just a projection in the first component. Right? And just the way I've set this thing up, you can see that it's a functor. Right? It's obviously, it preserves domains and codomains, it preserves identities, and it preserves composition, just because of the way that product category is defined. Similarly here, if you look at the arrow category, you can work out for yourself that there are two functors here. One that takes the domain of an arrow. So here's an arrow, and there's a functor that just takes the domain of the arrow. And there's another one that takes the codomain of the arrow. And now the trick is to show or to observe that those things really are functors. So those are some examples there of functors on those derived constructions, we have another kind of example. Yep.
Would key arrows still be a category if we left off either alpha 1 or alpha 2?
What would it mean to leave them off?
Key arrow is including this alpha 1, alpha 2 in the map.
So an arrow, the definition of an arrow from
Do it right here. So here's F, right? Let me write it like this. And then I'm saying, what is an arrow from F to G in the arrow category? C arrow. What is this? And what I'm saying is, just to transpose the picture to make it, just to get your head working in a different way, because sometimes it's good to think about things in different ways. So here now I've written this object over here, and here's this other object over here. A prime, okay. B prime. Here's this other object over here. And now I have to say, what is an arrow from here to here supposed to be, right? And what I've said is, well, it's by definition a pair of arrows, one here and one here. Give them some names, alpha 1 and alpha 2, such that this square commutes. So I don't know what it would mean to leave the alpha 1 and alpha 2 off.
meters. Is that okay?
Yeah.
Another kind of category is called a slice category. So take A to be any object in some category C. Then we make a slice category. This is going to be, and this comes up all the time, strangely enough, but it's going to be used in the very last lecture when we do the categorical semantics for dependent type theory. A slice category, which I write like this, C sliced over A, has as objects, it's kind of like the arrow category, arrows, but they're always arrows with A down here in the codomain. And then as arrows, here's another one. As arrows, it has commutative triangles. Arrows. The objects are the F's, and the arrows are the alphas. Okay, so instead of the rectangle, we just require, you can think of it as requiring this to always be the identity map down here. And then this is a special case of that. Okay, and then it's a category for the same reason as the other one is a category. And there are some interesting functors here. There's a functor, kind of a so-called forgetful functor. It goes from the slice category down to C itself. It just says forget this indexing here over A. It's basically the domain functor, right? And another thing that you can do is this. Look, let's suppose we have a map here. Let's make this our, let's make this FG alpha, what am I going to call this? K here, from A to A prime. Given any map like this, I get a functor C A to C over A prime. I'll call this K shriek. How does it work? So this is just an object in C. This is an arrow in C. This is a whole category, right? And now this is a functor from this category to this category. It works like this. Here's A. Here's F, G with its domain and codomain. And it works by composition. Here's K. So if this is a commutative triangle, now I take this commutative triangle over here to 1 over A prime. I just compose with K. So this is my definition of K shriek of F. It's K after F. Similarly here, k shriek of G. And now, if this triangle commutes, well, this one commutes by definition. This one commutes by definition. And so this is a little diagram chase, right? A diagram chase says you have to show that two arrows are equal, namely this one and this composite, because that's the definition of an arrow, right? An arrow from this composite to this composite is a thing across the top on the domains, making the outer triangle commute. But we know that this one commutes, and this one commutes, and this one commutes. And so to show that this composite is equal to this arrow, we can go like this. We say, this composite that we're interested in is really the same as this, followed by this, followed by this, by the commutativity of that triangle. That's the same as this followed by this, by the commutativity of that triangle. And that's the same as this arrow, which is what we wanted to show by the commutativity of that triangle. So that kind of arguing on diagrams is a very useful technique when you have to do kind of equational reasoning in a complicated situation. Of course, you could just do it with equations, but the diagram helps you keep track of what order to do the equational reasoning in. It's just a simple example, but you can imagine much more complicated examples.
Yes.
Is there some symbol that you're using there for the functor that you built out of K? I can't see it.
Shriek.
Bang. Bang? Okay, all right.
And I'm told that Whitehead called it shriek. And what's the name for this whole widget? The whole widget is the slice category. And I'm just observing that the slice category is functorial in this argument. And now you can go even further.
I said for each object in the category, you get a category. So we're fixing C. Now, for each object, we get a category, C over A. For each arrow, A, B, we get a functor, C, B, K, shriek. So we have an assignment that takes objects to categories, arrows to functors. This is living in C. What is this? That's a category, and that's a functor. That's a diagram in cat. Cat is the category of categories. It has as objects categories and as arrows functors. I didn't mention that one before, did I? But it's obviously a category, isn't it? The objects are categories, the arrows are functors. The composition is just composition of functors. Okay? It's like functional composition because these things are functions in each argument. And because of the way I've defined it, just like for posets, it's associative and it satisfies the unit law. So that's a category, full stop. And now this assignment is a functor. It takes an object of C to a category, it takes an arrow to a functor, and the whole thing gives a functor from the category to the category of categories and functors. That's a homework exercise for you. Good. Just to kind of keep all the balls in the air, right? Just to get used to these concepts. Anyone have some foundational queasiness at this point? Yeah.
One more time.
What's that?
Could you go over that last thing one more time?
What this is?
Yeah.
This is the category C. Here's an object of C. Here's another one. Here's an arrow of C. Mm-hmm. Okay? I've given you an assignment for each object of a category. Namely, the slice category consists of these triangles. And then for each arrow, there's a functor which goes from here to here. It's this functor. Okay? It's this operation. It takes triangles over A to triangles over A prime. And now I'm saying that assignment, which takes objects and arrows to categories and functors, is itself a functor from the category C into the category of all categories. The objects of categories are we have kind of 3 different levels going on here. Yep.
So I don't quite have the intuition for the slice category and the forgettable functor.
It'll come. Just do the homework exercise.
Okay.
We'll have some intuition later on when we talk about dependent type theory. The intuition for the slice category, really, or at least one intuition for it, is that you think of these things as families varying over this index. One intuition. Think of this, if this is a continuous function, for example. Now there are some points here, and for each point, you look at the preimage of the point up here, and that's a family varying in a parameter of the sense. So we'll talk about that.
Have you talked about fold X yet? No.
No.
Okay.
All right? Yep.
You asked if we had foundational issues, and of course,
Yes.
cat
Everybody
is
feel
too big.
foundationally queasy here because the objects of this category are categories. Here's a category. So maybe this is an object in that category. Right? You can think about it. I mean, at some point you have to deal with these kinds of questions. And one of the ways of dealing with them that's at least allows us to get some work done is to say, we'll define.
So we fix some foundations, foundational system. Oh yeah, okay. Here. Okay, so we'll make this large. Okay. Maybe set theory, type theory, maybe even category theory. Just fix some foundations, right? Fix some foundations, and then if a category consists of, so C consists of the objects and the arrows, there's a notion of smallness with respect to any of these systems, right? A small category would be one where the objects and arrows form a set, or a type, or an object in the category, and so on. So we'll say this is small, so as a definition, if both C0 and C1 are, let's say, sets, just to be specific. And we'll say it's large otherwise. So that's just a terminology, right? But it's a useful terminology because here we would say cat is the category of all small categories. And then cat itself is not small, right? By kind of foundational principles, cat itself must be bigger. And then it will be... Yeah, sure. It's beautiful, isn't it? There's nothing wrong with that, yeah. So, I mean, you have to get around these foundational issues somehow, but that's not category theory's problem. That's the foundational issue. Yep?
C over A, or?
Yeah, C over A, or C sliced over A.
So it's C sliced over A, objects that are arrows into A?
Yeah.
From E, from what? From anything else?
Arbitrary objects.
From any other object in C?
Yeah.
Okay. But not from any category?
No, that wouldn't make any sense.
Okay. And arrows in C sliced over A are?
Commutative triangles in C.
Okay.
You good?
Sliced over A means we don't use stuff from A, right?
No, it just means it's just a word. I mean, the objects of this category are arrows like this in C. So arrows, the codomain of which is A. Okay?
So the arrows in the slice are a subset of the arrows in C.
Yeah. If it's small. If it's not small, it's not a set.
Sorry? I don't understand what slice means.
What slice means, okay, don't be confused by the word slice. It's just, we have to call it something. It says some. Okay, good. So C over A.
Objects, let's do it like this. the objects of the new category C over A are pairs consisting of an object of C together with an arrow into A. And so the A is fixed here, right? So they're pairs like that, X, F. And an arrow in C over A is an arrow, so from such a pair. I'm not going to write them as pairs, though, because it's too, what's the word I'm looking for? Well, anyway. To write them as pairs is to kind of forego the advantage of category theory, which is that we have these diagrams to work with, right? I could write them as formal pairs and so on, but really they're things like this. And then another one is a thing like this. So now what is an arrow from a thing like this to a thing like this? Well, it's an arrow in the category alpha from X to Y such that G after alpha equals F. That is, this triangle commutes. So that's the definition of the slice category. The objects are arrows. The arrows are also arrows, but they satisfy certain conditions. Good? Yes? Didn't I say that? Here. For a fixed object in C, we make a slice category over that object.
And that last statement there, that only makes sense in the category C, but not in the category C over X. Yeah.
Yes. Yeah.
Right, because, okay.
That's the definition of the arrows of the slice category. Yes. Anyone interested in the slice category?
This is just a notational question. You're writing like little quote marks inside the diagram. Is that notation to say it can
Equal sign. It's an equal sign.
Oh, okay.
I just mean equal to those. I just mean this composite is equal to that.
Okay.
Yeah, good question, yeah.
Is there a good name for the dual of the slice category where you have arrows?
So we'll do duality tomorrow.
Okay.
Yeah, the dual of anything is a code of anything.
Okay.
Unless it already starts with code. I mean, I'll say code of language.
I mean, slice is fine.
What are we doing? I think I have to do representable functors now. Oh, yeah, foundational issues. Well, we'll talk about that later over a beer. No, I said the cat is, once we have a foundational scheme, then relative to that foundational scheme, we can define a notion of small and large. Then cat, we will say, is the category of small categories. Cat itself will not be small, typically, in most foundations, unless it's something perverse like Quine's new foundations, where cat can be an object in cat. Then typically cat will be large, and that's all. So that solves that evident puzzle, that apparent puzzle. Yes?
You've assigned us for homework.
Yes.
Is a large functor?
No, there's not a notion of large functor. There's a notion of functors between small or large categories, and it's a functor that makes a small category. Good. Opposite.
Here's a fascinating, but how much time do I have, by the way? Oh, great. Okay. Perfect. In category theory, there's this amazing duality. And it's really, on the face of it, the first time you see it, you think, oh, that's kind of cute, right? It's like a trivial or simple thing. But I claim it's actually a deep mathematical phenomenon, this category theoretic duality. But you can only see it through the lens of category theory. So we'll have a glimpse of a couple of instances of category theoretic duality in a couple of the later lectures. And maybe, or if you remind me at the end, I'll give you a few more pointers on duality theory. But so just to get started here, every category C has a dual category or an opposite. I'm going to use the term opposite. C op. So it's just a superscript op. And the objects in C op are the same as the objects of C. Actually, the arrows in C op are the same too. But you swap the domain and the codomain. Domain is codomain, and the codomain is a domain. This is kind of weird here, isn't it? So this is in C op, and this is in C. So the idea formally is this. If I have some diagram like this, B, C, G after F, and the identities are the same too, by the way, and this is in C, then I can regard that as a diagram in C op with the same objects, but I regard the arrows as going in the other direction. That is, I draw them the other way around because this is, although it's the same arrow, I swap now what is its domain with its codomain. So this is an arrow in C op, that's an arrow in C op, and now the composition you'll see has to be reversed because, let me give it a name, I'll write G bar to mean the same arrow regarded as an arrow in C op. And I'll write F bar to mean the same arrow regarded as an arrow in C op. But now if you look at the composition, it looks like this. It's F bar after G bar. And that is then the bar of G after F. So you have the same composition, but we've reversed the roles of domain and codomain. The one stays the same. So that's the notion of the opposite category. It's, if you like, it's really the same category. You just hold it up to the mirror or something like that, and you look at it from behind or something like that. So it's a purely formal operation on the category, but it's very useful. And like I said, it initially seems superficial, but we're going to make use of it, and you'll see what it's good for. For example, one thing it's good for is this. A functor F from the opposite of a category into another category is something like this. It takes a diagram in C to a diagram in D with the arrows all reversed. Right? Because really, if this is in C, say, well, then in C op, the arrows are going the other way, and now I make a functor, and the arrows end up going that way. Okay, so that's F of F, say, and so on. So this is the notion of a contravariant functor. Contravariant functor. A contravariant functor is not a different kind of functor. It's just a functor on the dual category of the category in the domain. We don't need a separate theory of contravariant functors. It's just functors where you swap the variance here in the domain. Okay? So that's one example of the notion of a dual. And let's have some examples of contravariant functors. So let's look at the category of sets. And for any two sets in the category of sets, you can build the set of all functions from one to the other. So here we are in sets. And we have some sets here, A and B, and then B to the A is the set of all functions from A to B. And now let's observe that this is a functor. This is a functor in the argument B. That is, for fixed A, I get a functor like this. F, I use the Shriek linear, F lower star from any, oops, sorry. No, that's right. From F from X to Y. So given any F from X to Y, there's an induced map, F lower star, from A into X, A into Y. What does it do? Well, it takes some G here in this, and it maps it over to F after G. Right? G is going from A to X. F after G is going from A to X to Y. That's where F lives. And this is f after g. Good? So now I claim that that's a functor. That's going to be a homework exercise, I think. This is a regular old functor. Look, the direction is going the right way. But you could also fix the other argument. So this is a contravariant functor in the argument a. So what does that mean if I take given, so in the argument a, so what that means is if I fix b, I have, as before, f going from x to y, I'll get a map from by to bx, which I'll call f upper star. And how does f upper star work? I take some y into b, and then I have here my f, and I precompose now. Here's g, and here's f upper star of g is precomposition, g after f. So that takes a thing from y into b over to a thing from x into b. And this thing is a contravariant functor of a. It acts in this contravariant argument. Okay? So those are just claims. You can check them as homework exercises. And in fact, there's a generalization of this, which I'm going to need, and which is anyway good to know about because it's a very important construction. And that's the notion of a representable functor. Yep?
Yeah, it is a bit late. Let's talk about afterwards.
What's bar?
What?
What does the bar mean?
No bar.
F bar?
No bar.
Oh, on the far left.
Why before?
Oh, it just means in the opposite
Let's talk
category.
about that later.
It's the inverse. Sorry.
No, it's not the inverse. It's a formal. It's just a formal tool. I'm not saying take a different function and come back to the inverse. I'm saying regard this function as having, regard this arrow as having other domain components. Okay.
Representable functors. This was a construction in sets, right? I take some sets, I take A and B, and I return this set. So this is a special case. A more general case is I take some category C, and I take some objects A and B in C. Okay? And now I make the set, which I'll call HOM, C if I need to be specific. So this is the set of all arrows from A to B in the category of C.
Why is the set?
Because I'm assuming that C is small. If I ever say that something is a set, it means I've assumed that it's a set. Okay? So I assume that this thing, that C is small. I take this collection of all arrows like this. So you see, things are a little bit different here. This was a special case. This lands back in the category I started with. That doesn't have to happen. This lands somewhere else. Okay? But just as before, I can say fix A, and then I get a functor in B, HOM A blank, and that will take HOM A B into HOM A B. Well, let me say X here. X and Y. X and Y for any X goes to Y, just by composition, just as before, by composition. Right? If I have a map from X to Y in C, and I take an element in this set, well, that's just some thing here coming out of A, and I compose, and I get something like this in this set. So that's my functor. It's called the representable functor of A. Representable functor of A. And similarly, if I fix B, I get a contravariant. So where does this go? The representable functor goes from C into, so the functor looks like this, HOM, I better write bigger, right? So the representable functor of A, representable functor of A, I want to emphasize this, is hom a blank. It goes from C into the category of sets. Right? It takes an object x to the set of all arrows from A to X, and it takes an arrow f to the function given by composition. That's a representable functor. And there's a contravariant representable functor. Covariant. Covariant. And just as in sets, there's a contravariant representable. This was fix A, now fix B. What I really mean is fix the first argument, fix the second argument, right? Fix B, and we get blank B. This is arrows into B, and it goes like this. It takes I'm just doing the set thing that I did before, but I'm doing it with these so-called hom sets rather than with sets, X, B. That's a map, F upper star. It comes from a map going this way from X to Y, because this was maps from Y into B. So I take something here, and I precompose, and that gives me something over here. So this is the contravariant. Contravariant representable functor. These are really quite important, and you'll see later on what they're good for. Contravariant representable functor. So that's B. It's contravariant in the first argument, and so that's going from C op into set. Maybe that's all I need to say right now. So you have some homework exercises, and you'll get used to these representable functors. I think a homework exercise is to show, in fact, the whole thing hom is a functor on the product category into set. And these are just its two parts. And later on, when we have a little bit more information, we're going to start looking at things of the form set to the C, the functor category, the objects of which are functors from C into set. The arrows we have to determine, those are called natural transformations. And then we'll see that, for example, we can have contravariant functors, and we can have C itself maps by this operation. It's basically the currying of this hom functor, and that's an important map called the Yoneda embedding. So by the third lecture, we'll have the all-important Yoneda embedding. It's been said that category theory is really the theory of the Yoneda embedding. You can do lots of things with the Yoneda embedding. So we'll look at that later. Okay, that's it. Thanks. Homework exercises are on the web, so either go to the program webpage. There's a link that says curriculum, I think. Yeah, and then there's a link to my lectures. If you go there, I've made a little page, and it's got some problem sets. The other way to find it, I think, is through my home page down at the bottom. There's a link to the summer school here. And then you go to that page, and then you've got the lecture notes and the problem sets. I'll be around to talk about the problems with you. There was a doodle poll where some people said that they're already quite advanced in category theory. So I know you're here. I don't know who you are, but there are at least 4 of you, I think, who said you already know some category theory. It'd be great. Maybe you want to raise your hands if you're confident about that. It would be great if you're around to help people, too, with questions that they might have about these exercises, because I didn't, unlike some of the other speakers, I didn't bring a student with me to act as a TA. So you can be my appointed teaching assistants if you want to do that. Maybe raise your hands a little higher so people know who to ask if you get stuck. These are your expert consultants, okay? Find the one nearest you, and that will be your person. Thanks.